Yeah, thank you for the invitation.
I'm glad I can finally be here. And I talk to you about reconstruction and its inverse problem, sampling. And to start, I give a very simple example you may know from your childhood, the game Connect the Dots. It's an easy and fun game. But what if there's more points, and what if we drop the numbers? Can any of you have a guess what this shape is? Pardon? Okay, it's a dragon. Yeah. So it's hard for us humans, and it's even harder for computers, for algorithms. What we are guided as humans are, for example, Gestalt laws from psychology. We have if we connect points, then we're guided by a principle of connectivity. So we want to connect close by points. Continuity, so having the same direction, little angle, and also closure. So we want the closed curve because silhouettes of physical objects, boundaries, always closed. And it's actually an ill-posed problem because there's many possibilities how to connect these points, and we don't have a clear answer how we should connect these points. So we need some theory on how to do that. And of course, in 3D, this is a much more important and more complex problem. You can see here. So this is for illustration, some simple, nice data. But if you go to reality, this is a scan from a small town in the north of Austria. It's 50 million points. There's scans that have billions of points. So there's a lot of redundancy. And we don't need all the data because if you have structures, they have a lot of points because the density of sampling is similar, and we don't really need it. Also, if virtual models get designed by artists, then they use a few control points to design the shape, but there's a lot more points in order to create the curved surfaces. And so by sampling, so you have a boundary in the physical world, which is continuous. And if we use a laser scanner or some other device to sample this, then we get discrete samples. Here, some points on the boundary, same in 3D. And we want to reconstruct the connectivity. So the edges between these points, in 3D, it's a mesh. And as you can see here, we don't get the full information. Don't know if it's visible here. It's very close to the original curve here, but of course we only get the polygon here because we just have the connectivity. So what we can do is we can sample here again, and in that sense, it's still there. So what we need is possibly as few samples as required for the connectivity, also to reconstruct the geometry well that's needed, remove redundant samples, and this defines a sort of sampling condition that's required for the reconstruction. We'll first talk about reconstructing, then go to sampling. So this is a detail of the scan I showed earlier from the town place of Retz, and there's some challenges here in real-world sampling. We have non-uniform distances between the samples because the laser scan might go at a very sharp angle to the surfaces. Then we get large distances. And this is a problem if we have very thin surfaces, and we might want to connect close points. If they are large distance and the thickness of the surface is very small, then they might get wrongly connected. Another problem is outliers. If you have a laser scan and it points to a window, then it will go to connect, only get reflected at the next surface, which can be very far away. And because compute the position as the time that's needed for the laser, time of light coming back, the point will get positioned somewhere completely elsewhere than we want. So this is 2 points is what we want to eliminate. And there's also always noise with sensors. They have a certain probability to arrive at the curve, but not exactly. We can know this noise from the sensors, and this is exactly on the curve, and then we somehow smooth it or fit it. And also there's a problem of missing data. For example, here or some other specific data is just missing because it was in a scan shadow. The scanner never saw this, so we need to somehow deal with this. If you look in Google Scholar, there is over 500,000 of papers with the keyword surface reconstruction in the title. So this is quite an important problem in the last 10 or 20 years. And I start with a planar problem because it's much easier to illustrate, and this is where I started working on. So in the beginning, so you see again, a set of points, a reconstruction, and my original hypothesis was that the minimum length boundary is the best for a good approximation of the shape of the points, because we don't know exactly. This is a hypothesis. But this corresponds to the traveling salesman problem, as some of you may have noticed, and this is NP hard, and this is not feasible to solve. So what I did here is points. Then I construct the Delaunay triangulation. Delaunay triangulation is a triangulation of the set of points. And as you can have a lot of different triangulations, the Delaunay triangulation is unique. It has the property that for the 3 points in a triangle, if you use this on the triangle, it will never contain any points. We have a unique Delaunay triangulation for each set of points. This is also generalized to higher dimensions. And the bold lines, bold edges, are the minimum spanning tree. It is connecting points with the minimum length edges. You get something like this. All this can be done quickly. And then we do some heuristic, exchanging edges, adding edges, and then because hull is manifold, meaning each vertex has incident edges, so it's like a bounded shape, but there's also edges inside. Then we have to remove some edges, then we get the manifold. And we prove that it reconstructs the minimum boundary, but in many cases it's still too slow, because we can solve the traveling salesman problem to get around the NP hardness. So the next approach was to try to get close to this minimum boundary, minimum length boundary, but do it fast with a guarantee. Again, we start with points, and then we do the Delaunay triangulation that I mentioned earlier, which we don't see here. And then we create something called boundary complex. This is like the minimum spanning tree. So for each vertex, we connect it to a spanning tree, but we add edges with minimal length, such that each vertex has at least 2 edges. It's the property we want for the manifold boundary. So we have the Euclidean minimum spanning tree is a subset of the complex, which again is this is fast. But then, for example, this here is not manifold. It's like squeezed together. So what we do here, we apply an operation that we call inflating. We add triangles from the Delaunay triangulation with minimum standard boundary length until we get something that has a manifold. But we still have points inside. So we designed a dual operation, sculpting, where we remove triangles from this boundary, from the outside, to the interior points to free them. And then again with the minimum length criterion, and then we get a boundary which is not the minimum boundary, but often very close, and it's fast. So this works in log n time for n points. So this is already good, but we can only reconstruct closed shapes. So if we have several shapes in the point cloud, they will always get connected, and this is not what we necessarily want. So we were looking for some local algorithm. We found something very simple. We have a point P and its neighbors, distance, and 0 and 1, and so on. So we connect with the nearest neighbors. This is always a good thing from the principle of connectivity. And then we use the midpoint of this edge, create a half space, and then you connect to the closest neighbor, which is on the other side. Avoid to have very sharp angles. Then it guarantees that we have never angles smaller than 60 degrees. And also, these points cannot be closer to each other than this point P. So this gives us very good results on sharp angles, as you can see here. And it manages not only to reconstruct several shapes in the point set, but also open curves. Also, there is a guarantee for a sampling condition, which I will explain later, that corresponds to the size of the local feature. But then we have also noisy points. So the next thing was we do a scan. Here we have a scene, and then we have the depth image, and which encodes. So for each pixel, we have a distance to the point in the scene, and this is encoded by shade. So the lighter it is, the farther away is the point. Then we can segment objects. So we have monitor up and the mouse, and then we have some boundaries from these silhouettes from the segmentation. But these are very noisy. Here on top of the monitor, we want to reconstruct a nice shape. And so we have a curve C, the red curve, and the points are not exactly on the curve. So the idea is first to still connect the points, and then separate the low frequency curve from the high frequency parameterized along the curve, which is the noise. And then we can smooth the noise by just projecting these points on the connected curve. The hypothesis on this is that we can recover all features that have an extent which is larger than the noise. This is similar to the sampling theorem, which lives in what we do here is, as the algorithm I showed before, we locally connect to the nearest neighbor and then to the half space. And if the neighbors have multiple edges, then this is the boundary. But what if the points are noisy? I can have several neighbors. There can be noisy clusters. And so what we do is we fit a circle, and then we project the points, the noisy points, on this circle. Then we have an ordering, and then we choose the point on each side of this point we're looking at, and then we can apply the same thing. So we have points similar to here, and then we connect them. So there's also a question how to choose the neighborhood. We do some incremental stuff. I won't go into the details here. So for the results, we have some noisy points. On the top and bottom, there is almost no noise. And left, right. We get the connectivity. It's the topology of a circle, but it doesn't look very nice. And from the fitted circles, fitted arcs here, we can also get the variance of the noise. You see on the top and the bottom, there is no noise detected. Here you can see the extent. And then what we do is we blend these arcs together, and then we get the result that looks close to the circle that we and perturb them with a lot of noise. So and we improved this because we did not just want to blend the points from sensors. We know how much noise there actually is. We know how much they can deviate by distance. Larger distance, there can be more noise, or also the angle, also material. So basically, for each point, we can associate something, a probability density function, which you can imagine like an ellipsoid in 3D space. And here in 2D, this is visualized by these gray circles. So we sample some points and perturb them with noise. And then we create, we construct the connectivity as before. And then we don't blend, but we move these points basically inside of this gray disk with some energy functional. I'm going to details here. And this is the denoised result. So we don't just smooth it, we try to actually remove the noise based on what we know from. With some real-world example, we have a color depth image of some device. And here we have the point with the noise, small gray disk. Here with the detail. We first get the connectivity, and then this is the denoised result. So I did a lot of work on curve reconstruction, and then I was asked by colleagues to, Stefan, you did a lot of work there, let's do some state-of-the-art report. And we collected 36 curve reconstruction algorithms. We categorized them by input they can, like, can they noisy data, do they produce only closed output, or can they also produce open curves, multiple curves? So we categorized them, and then we also created a benchmark. We evaluated 14 algorithms, which are available as open source. You can see one of the examples of the benchmark for noisy points, and with increasing noise here, from left to right, you see the results of the algorithm. So inside the red box are our algorithms, especially the two on the right here. The last ones I presented perform quite well for noisy data. And what we use as input data is classical point sets like from papers, what other people used, then silhouettes from images, sampled curves, open, intersecting curves. So we thought this field is finished. We did everything that was to do. And then my PhD student, who, by the way, graduated yesterday, improved on these results. She found a graph that was proposed in the late 80s, the spheres of influence graph, which is very easy. Basically, you connect points with an edge if their distance, that edge, is smaller or equal than the cumulative distance to their nearest neighbors. Simple, it extends into n dimensions. She improved on the results. And something else, we also tried to 3D, and it's not finished work, but what came out of that is we analyzed meshes, and we look at the connectivity, try to reconstruct the connectivity. There's the k nearest neighbor graph, where you find, for k, for example, 3, you find the nearest point, the second nearest point, the third nearest point, and then you create a graph. So this works very well. This is used in many applications, but you need to choose the number of k. The user needs to choose, or you need to choose for the application. And the spheres of influence graph does not need a parameter. It has this advantage. And when we analyzed how it overlaps with the original mesh, with the ground truth, this gives us even the best overlap compared with nearest neighbors k and n with different values. So this works better, at least for this case of mesh connectivity. It may work for other applications. I'll come to that later. And then we left the planar domain and we continued to higher dimensions. So what about if we have a curve? We want to reconstruct it if it's on a surface. Then we get all kinds of problems because Euclidean distance doesn't work anymore. We need geodesic distances along the surface. And since objects may have handles, like these throws, we cannot use a notion of inside-outside anymore that we use for curves. So we use the notion of injectivity radius. So intuitively, this is, we have a point P. This is the all where the injectivity holds if you map it to a planar domain. And we can use this for the curve reconstruction. So an application is in cultural heritage. So we have, for example, artifacts, and the archaeologists want to boundaries of these drawings. And they would need to draw all of this, or they can just mark a few sample points. And then our algorithm can just connect. It didn't work before. And this also works in other spaces, for example, in the space of 3D rotations, where we have a path flying around. And with many fewer points, we can reconstruct. We have a sampling, prove the sampling condition there. And now it's time to go to 3D surface reconstruction. So if you remember one of the earlier algorithms where we just we want to connect those points with close to minimum boundary, but very fast. We extended this in 3D. So we again create a boundary complex. That's not the graph of edges, but of triangles, because a mesh is made of triangles, boundary. And then we get something like this with artifacts. Then we remove artifacts by an inflating operation. And then we still have some, because the Delaunay triangulation in 3D is tetrahedra. So the gray areas you see here, there is some tetrahedra. So it's not a unique surface. So we want to remove this. So we do a sculpting operation, and then we end up, in many cases, with a manifold mesh. This can reconstruct very sparse samplings. You can see here the ears, but we were not able to prove anything. Next, we applied machine learning, because this came into fashion. And what we did here is that we said, okay, if we decompose an object into very small patches, these patches, we have like thousands or 10,000 patches. These are repeated in all kinds of objects, and if we can learn on that, then we can just infer the configuration of the points, even for very noisy data. But we also need the global orientation, because what we expect is output from this network is a signed distance function. That means for each point in space, we want to know the distance to the surface, and if it's inside or outside, giving a sign negative for inside, positive for outside. So we train with global points for the sign, for the inside-outside orientation, and for the local shape with small patches here. And then we infer a point, the red point X, into the network. We do the local and the global inference, and then we get the sign. We combine these two, and we get this sign distance function. Tells us for this point surface, and it's positive. When we have many of these points, then we can apply a meshing algorithm to the sign distance function, and then we get the output mesh. So here you can see some result, very noisy point. This is the ground truth, and it manages to recover. But this is very, very slow compared with other algorithms. Another 3D surface reconstruction algorithm that we designed is based on a very simple condition. We were looking at the Voronoi diagram. This is the dual to a Delaunay triangulation I mentioned earlier. Basically, you have 3 points in 2D, the triangle. Then you have this circumcircle, which does not contain any other point. In the center is the Voronoi point, the center of this ball. And if you look at the interior balls, they are shaded right here, and the exterior, which are shaded green, and we can see the denser the sampling gets, the less overlap is between the interior and the exterior balls. This extends in higher dimensions. What we do here, we look at the ratio of overlap. The balls can also be of different size, and then we fix a variable, a value, and then we get very good results. So missing data, sharp features, noise, outliers, and scans and handles, as you can see. And we managed to parallelize it, so it runs on a cluster even faster. It runs about the magnitude faster than other state-of-the-art published last year, and it's about the same quality. If you run it in parallel, it's even faster, because the Delaunay triangulation has the property that we can divide it with some overlap, and then we get the guarantee we reconstruct it, divide and conquer locally, then we can merge it and we get guarantee for the same. So now we come to sampling part. And question, why do we want to sample boundaries with fewer points? Here we have a curve, continuous curve, then we have some samples. But each sample has a cost, because we need to store it, and we need to process it. The more points, the more it costs. So if you have fewer samples, you're happy. You can see example. What we do here is we sample according to the feature size. So a feature is, for example, one of the ears of the bunny. So all these local things are features. So no matter how large the feature is, if the ear is small or large, the idea is that we can just place the same number of samples and we get the same quality of result. We can see different number of samples and it gets denser and denser, all proportional to the size of the feature. What is this good for? You can see here, there are some boundaries, and in spaces where there is no boundary, we can, so this is good for simulations like finite element simulations, and if you need to compute all the elements and the relations, the fewer elements you have, the faster you can run it. So if you have larger elements, where we have no small features, then we have less elements, and then we can. Another application is different. So when you color sketch and you have open boundaries like here, then when you click inside in the paint program, then the color will bleed outside, and this is not what you want. So what we do here in the background is only triangulation like here, and then we get all these open boundaries off. So if you here, and we can also analyze curve reconstruction algorithms, because before in our benchmark we did it with data, real-world data, data that we collected, but we did not have an analysis on a theoretical condition. Here we have some value. It's called epsilon. It's related to the local feature size. I will explain that in the next slide. And based on that, we can quantify how well the algorithms perform by having an epsilon sampling. So it gives us different number of samples, and then seeing for a number of samples if the algorithm can reconstruct it correctly. If yes, then we get this 100% down. You can see here some algorithms, they large values, and others not so good. Now for some theoretical stuff. So the local feature size, if you have a curve C, then the red medial axis, you can think of it as a sort of skeleton, is the set of points where that have at least 2 points of equal distance on this curve. You can imagine you have a disk with the center on the axis, and you move it along this skeleton. It gets larger and smaller. Some places it gets very small and small features. And this is the medial axis. Then, if you take any point P on the curve, you take the distance to the closest point on the medial axis. This is called the local feature size, and this tells us how large the feature is. So here it's large, and here it's very small. And once we have this, we can this epsilon sampling condition was constructed. So for any point on the curve, we also have samples, and so there's the distance from a point to a sample on the curve, and this distance must be smaller than epsilon value times the local feature size. Smaller epsilon is, the more samples we need, because then we must get closer to the samples. The samples must be closer to each other, because otherwise the point has too large distance, and the larger epsilon gets the fewer samples we need. This is called the epsilon sampling. That will be important for the next slide. So we looked at some sampling conditions for reconstruction algorithms. One that has epsilon up to 0.2. You see, it needs a lot of points. And then we were able to prove with the algorithm, the small, simple local algorithm I presented earlier, that we can manage up to epsilon up to 0.47. This was too complex to prove in the classical way. Would have to write a very long proof. Reviewers would have to check it. So what we did here is we did a computational, computer-assisted proof. So basically, we have a point here, sample, and then we have a hypothetical next sample, depending on the angle to the next point on a curve. Important thing is that the black point must remain in this blue space. So we analyzed this for this multidimensional solution space and checked for the steps in each dimension if the black point was always in the blue areas, and we came up with this epsilon, which is correct. But we were not entirely happy with that because the local feature size, which is used in this epsilon sampling, which has been used in several papers, has a large variance. Because you have small features, then you have very large features, so it can vary very strongly. And that means there you need more points than that would be really necessary. If I go back here, you can see like here where it changes, there's more points would need to, that we assume we would need for reconstructing the connectivity. If you think we have fewer points, we could still reconstruct it. So we were looking if there's something better. And we came up with a different sampling condition, which we call rho. So instead of using the local feature size at a point, we look at the interval along the curve. And this is called the reach, which is the infimum of the local feature size inside this interval, for example, E and S0. And this showed to be a much more relaxed condition. So you see 0 points here. The rho goes up to 0.9. And we also managed to prove a relation between the rho and epsilon. So how does the sampling work? As I said before, there's a curve, there's the medial axis. But the medial axis is invisible to exactly reconstruct, except for very simple shapes like a circle or ellipse or something like that. So what we do is we take many points along the curve, then we grow a tangent disk until it hits the curve at some point, because then we have 2 points at least, and then we know the center is on the medial axis. So we produce a lot of points here by boundary, back, and then we connect them in a piecewise linear curve. So this is just limited by numerical precision, and of course by the amount of runtime that it takes to sample thousands of points along a small curve. Then, for a point, we can compute the local feature size by checking what's the closest point on this polyline that we have as medial axis approximation. We check the nearest neighbor point, and then once we have the local feature size, we can compute the epsilon condition, because the distance to sample needs to be smaller than epsilon times. We do this as follows. So we start with a point here on the curve, then we step along the curve until this condition is not fulfilled anymore. Then we go back to the previous point, interpolate, and then with a point where the distance is smaller than epsilon times the local feature size. Here, then we construct the disk and take the other intersection as the next sample. And we start over with this as sample point 2 and do the same thing over until we have sampled the whole curve. So this is also interesting in 3D. Here we have, you can see a mesh that is epsilon sampled. Here we have small features at the ears. So here you can see smaller triangles than uniform length mesh. With we apply a heat simulation. So we apply heat at the tips of the ear of the bunny, and then it starts spreading across the body. Look at the numbers, then we have epsilon sampling, for example, 5, which corresponds to this minimum length for the tips of the ears. We get a certain number of elements for the simulation. If we use the same number of approximate same number of elements, then we get this corresponds to this length, and we get a much larger root and also if we try to make all elements as fine as for the epsilon sampled, then we have over 100 times more elements. And also an application is similar to 2D, determine for surface reconstruction algorithms what kind of epsilon they can handle, or how many samples do they need in order to reconstruct this. Fail, have a large error, so this correct reconstruction because this is more complex in 3D, but and some algorithms, for example, aus the OH1 comes quite well until here you can see a number of triangles and here's some example of the reconstruction looks like. And there's how we sample in 3D. Again, we have a Delaunay triangulation, so the black curve S is sampled by the red dots. Then these are connected with triangles. These are the blue lines. And they are solid if they are on the boundary. And we have the Voronoi diagram, which is a dual, and which, for example, here you can see the 3 points of a triangle. Here's the circumcircle, and the center is the Voronoi point. If we connect this with another Voronoi point, then we get a Voronoi edge. And everywhere where this Voronoi edge crosses the Delaunay edge, triangle edge, you know that this is a edge of the boundary for specific epsilon values. Why is this interesting? Because if we intersect this Voronoi edge with the surface edge, it also intersects the boundary, the curve here. And then here we have equal distances. We can test the epsilon condition. And then we can decide whether it fulfills the epsilon sampling condition or not. And if not, then we can insert a point into the Delaunay triangulation and add a more sample to the boundary until we are satisfied everywhere and our sampling fulfills the sampling condition. In 3D, this actually looks like this. We have a triangle, the surface, we have the Voronoi edge which intersects, and here the surface. This is the point we would add. However, sampling requires a smooth boundary. There is, we applied it on meshes, but this is not exact. So one possibility is the sign distance function, which I mentioned earlier already. So sign distance function, we have any point in space for 2D or higher gives us the distance to the boundary and assign this indicator whether it's in or outside. So if we color this, so the blue values are negative, they're inside this rapid outline. And this has a property that it's a smooth boundary. So we can, or we can use subdivision surfaces. These are used in animation films, for example. So artists design coarse mesh, this, and then this is subdivided and getting smoother and smoother. And there's also a limit surface that you can compute directly. And then we also have a smooth surface that we can use for sampling. How we do this? We take a point on the boundary, then we have a tangent ball, and then we shrink this until it only touches a point, 2 points on the boundary. Then we know the center is on the middle axis, and then we use this middle axis as in 2D to compute to use this approximation to compute the local feature size. So this, now I do a conclusion. So I talked about connecting points in 2D, connecting points in 3D, sampling in 2D, the inverse problem, sampling in 3D, smooth surfaces, which is ongoing work, and how to deal with huge scans. This is work in progress because we can apply some distance function there. They are open, so we need also to deal with visibility, and we need to reduce these billions of points to, with the sampling, to some reasonable amount of points. We can process them quickly with a mobile device. And also want to apply probability, like the noise of the sensor in 3D, and also integrate this inside distance functions or other. And the next step is to go into 4 dimensions. Like if you imagine a pulsating heart, this has spatial temporal data. This gives us much more challenges because we not only want to compress the 3D spatial data, but also with the temporal dimension. With millions of points. And also these spheres of influence graph I mentioned earlier, which better than KNN for some purposes and does not need a parameter. This could be an interesting graph neural networks or other which rely on k-nearest neighbors. So thanks to you all for listening to my talk, and also thanks to my collaborators, one of which is sitting here, Furan, and all the code is open source. You can find it on my website.